Hello grade 12s and welcome to our 6th lesson in our series on work, energy and power. In this lesson we're going to look at the definition of conservative and non-conservative forces, and finally we're going to look at the conservation of energy with non-conservative forces present. But as always, before we do that, let's look at the solution to the problem given in the previous video. Have you tried that problem on your own? It is vitally important that you work through this problem before you look at the solution. As I always say, science is not a spectator sport. You need to develop cognitive functions, and you do that by solving problems. Okay, so let's have a look at the problem. The simplified diagram below shows a slide PQ in a playground. The slide is 3 meters long and 1,5 meters high. A girl with a mass of 22 kilograms is at the top of the slide P. The girl accelerates uniform from rest, and she experiences a constant friction force of 1.9 Newton. Use the work-energy theorem to calculate her speed at the bottom of the slide. Work-energy theorem states the net work done on the system is equal to the change in kinetic energy, which means that is equal to the kinetic energy finally when she's at the bottom minus the kinetic energy initially when she was at the top. But before we do that, we need to calculate the total amount of work done, and in order to do that we need to know what all the forces are that's acting on this girl. So we draw a force diagram and we find there's a friction force, there's a gravitational force, and there's a normal force that's acting on this girl. There's no applied force, nobody is pushing her or pulling her down the slide. Okay, so we can complete our, or we can elaborate a bit on our equation. Net work done is equal to the work done by the friction force plus the work done by the normal force, which by now we know is 0, plus the work done by the gravitational force, and that is going to be equal to the final kinetic energy minus the initial kinetic energy. Okay, so let's go and fill in some of these values. We know the work done by the frictional force is going to be equal to the force times the distance that this force is acting on. It's 3 meters, cos the angle between the force and the direction that it's traveling. It's traveling down, the force is going up, so the angle between those two is 180 degrees. By now we know the work done by the normal force is 0 because the angle between the normal force and the direction that it moves is 90 degrees, and cos of 90 is 0. And then the gravitational force, the work done by the gravitational force, we also know by now that the work done by the gravitational force is just given by the mass times the height times the gravitational acceleration. You remember we proved that in a previous video, and in this video we do have the height, so it's nice we can use that one as well. Okay, and then that is going to be equal to our final velocity, which is 1/2 times our mass times our final velocity squared. Sorry, I said final velocity, I meant final kinetic energy, minus our initial kinetic energy. They tell us that this girl is traveling from her rest. Oh, I always love it when there's a 0 in a term, because that means that whole thing becomes 0 and we don't have to calculate that. So we've got numbers here that we can calculate on the calculator. We've got only numbers here. So the only unknown that we have is this V final, which is what we need to solve. And when we solve this, we find that our velocity is 5,37 meters per second. Okay, so let's have a look at what exactly conservative forces are. I just refer to the fact that when we calculate the work done by the gravitational force, it is equal to the mass times height times the gravitational acceleration. And I think you can remember from a earlier video that I told you that in these 3 cases, if all 3 of these boxes were on the same height, in all 3 cases, the amount of work done by the gravitational force would be exactly the same, regardless of whether this box travels on this long slope or this very short one or the medium slope. And these types of forces where the work done by the force is not really dependent on the path that, like you see, it can take a short path, it can take a long path, it doesn't really matter. That type of force is called a conservative force. A conservative force is a force for which the work done in moving the object between 2 points is independent of the path taken. Now, I'm sure a lot of you will say, no, this is not possible. It cannot be that the amount of work done to take this mass down that entire slope cannot be the same as the amount of work done in just taking it this distance. And you are quite right, because you are referring to the total work done. I'm only talking about the work that's being done by the gravitational force going down. And that work done is absolutely independent of the path. It only depends on the initial and the final position of the object. Now, what other types of forces do we get that are conservative, where the work done by the force is not dependent on the path? Well, gravitational force, which you saw, is one example. And then also the force, elastic force in a spring. Whether I pick this up spring and go like this, and then extend it, it does not matter. The amount of kinetic or the amount of work done by that force at this distance will be the same regardless of whether I first picked it up and then took it down and then stretched it out and then brought it back to this distance again. On this distance, the amount of work done by the elastic force will be exactly the same. On this object. I remember, I'm not saying the total force, just the work done by the elastic force. And another example is an electrostatic force. When I have two charges near each other, you know that they either have an attractive or a repulsive force on each other. Now, if this is the distance that these two particles are apart, and I move this one a bit further, whether I move it up and down and to there, all around, and then let it stand still there, it really doesn't matter what path I took. If I start here and end there, the amount of work done by the electrostatic force will be constant regardless of what path I take. And that is the definition of a conservative force. Only conservative forces causes a difference in potential energy. Now, this is a new and foreign idea. You will learn. I think you have made contact with potential energy, with gravitational force already, where you know that potential energy is mass times height times gravitational acceleration, mgh. And you have also dealt with potential energy in electricity, where you deal with a change in potential in a circuit. But potential energy can only be associated with a conservative force, because potential energy has to do with the direction or the position of an object as well. But we will look into this more in our next slide. Potential energy and conservative forces. Now let's see what is the relationship. Here is an example of our different conservative forces. There is gravitational force that's going to do work, and then the work done by gravitational force. Here we have an elastic band that is stretched, and here we have a spring that is compressed. So these are all examples of conservative forces that can do work. Energy that an object has as a result of its position, that is the definition of potential energy. Now, if we say the potential energy is the energy as a result of position, then you must agree with me, then you cannot have that amount of work done is dependent on the path. We know, for instance, that if this block is sitting here, this block has a certain amount of potential energy with reference to the ground. It really does not matter where this block traveled in order to get here, whether it rolled down a mountain a bit to one side and then to the other side and it ended up here. The fact that it's here, that is what's going to define the amount of potential energy it has. With non-conservative forces, those are forces that where the force acting on the particle is dependent on the path it taken, there you cannot really specify potential energy, because potential energy is associated with a position, and as soon as the path you took to get to that position has an influence on how many work you were done, then it means that for different paths taken, you're going to have a different potential energy at the same spot, and that makes no sense. So therefore, it's important to know that potential energy is only associated with conservative forces, and the potential energy is the result of the work done by a conservative force. Okay, so that's just a slightly new view on potential energy. Okay, let's have a look at the work done by a conservative force. And we're looking at gravitational force, for instance. Now, if I have a mass that is sitting on the ground, its potential energy before this action is quite low. And if I pick up this block over this distance, then its potential energy increases. The force that is acting on this object is going down, that is gravitational force, and the direction that I'm moving is going to, in order to get that potential energy, is going to be in the opposite direction. So you can see that the amount of work done to get this block from the ground all the way up there is going to be equal to a negative number. That's my direction of motion. Now let's look at the same. So what I'm seeing is, in order to increase, or a high potential difference is associated with a negative amount of work that's done. Can you see the work that I did in order to move the block from here to there, and in order to increase the potential energy, was moving in this direction, which is 180 degrees in the opposite direction of the force. So the work done is going to be a negative number. The same goes for charges. Now let's just look at these two positive charges. We know that these charges are far apart from each other, then the energy, the potential energy before that, fear was for the Afrikaans voor. I forgot to change that to before for this video. So just imagine that this is a B and an A for not voor en na, which is Afrikaans, but before and after. Sorry for that. So the potential energy before, that should be a B, is low. But as soon as I bring these two charges right near each other, then the potential energy afterwards is going to be quite high. Now let's look at the force that's acting on this object. The Coulomb force that's acting, or the electrostatic force, that's the word that I'm looking for, is pushing away, because these two charges are the same and they repulse, but I'm moving in the direction opposite to the force. So can you see the angle between my direction of motion and my force is 180 degrees. So again, in order to increase the amount of potential energy, I do negative work. So the work done by a conservative force is negative, and the work done by a conservative can be given by negative the potential energy after, which is the high number, minus the potential energy that it had. So the potential energy of this thing over here, that's the energy of the block after motion. So this is a potential energy after, minus potential energy before, is that number. To get the amount of work done, that is going to be equal to the negative number of this energy. You can see that this potential energy is much more. Let's say, let's look at this example when it's on the ground, mgh, h is 0, so we know the potential energy over here is 0. And this one can be, it can be anything, but let's just say it's 200. So if we have the energy, the potential energy after minus the potential energy before, we're going to have 200 minus 0, and you can see that is a positive number. So the difference between potential energy before 200, for instance, don't worry where I got the 200. That's just an imaginary number that I had for calculating the potential energy up here, just to give you just to try and explain why this number is going to be positive. So I have a positive number here, minus 0. I see that that is going to give me a positive number, but now I just explained that the work done by the force is going to be a negative number. So if I want to know what the work done by the conservative force is going to be, it's going to be minus the change in the in the potential energy. Okay, so the work done by the conservative force is equal to minus the change in potential energy. Okay, so now let's look at the definition of a non-conservative force. With a conservative force, we saw that the work done by the force is independent of the path it takes between 2 points. But with a conservative force, with a non-conservative force, this is a force for which the work done in moving an object between 2 points is dependent on the path taken. So it really does matter whether your road looks like this or whether it looks like that. With a work done by a conservative force, we don't really care how this path looks. As long as we know we're traveling from point A and B, we can calculate the amount of work done. That was in the situation of gravitational force and electrostatic force and the force in a spring. But if you, for instance, look at something like friction force, it really does matter where you traveled. And that is an example of a non-conservative force. So typical examples, as I said, is friction. The fact that you have to move over this surface really depends on how long this surface is going to be. It's going to make a difference on the amount of work that you do. Air resistance, the work done by air resistance really depends on where this parachute is moving all the time with the air resistance. And something like tension in a rope, that is also dependent on the path that this object is taken. So all of these are examples of non-conservative forces. Okay, so now let's have a look at the work done by non-conservative forces. Now we can start by saying the total work done by an object must be equal to the work done by the conservative forces plus the work done by the non-conservative forces. Total work done is the work done by all the forces. And there's only two types of forces, conservative and non-conservative. So that's the first way that we can write down our equation. So for that we can say from the work energy theorem, we know that the total work done is equal to the final kinetic energy minus the initial kinetic energy. That is my work energy theorem. So instead of work title, I can write kinetic energy final minus kinetic energy beginning. We also just saw 2 slides back that the work done by the conservative force is equal to the change in potential energy. And we can just say for that the work done by the conservative force is just the work done by the conservative force. I just wanted to explain where I get this equation from. My total work done is equal to the work done by the conservative forces and the non-conservative forces. But the total work done is the change in kinetic energy. And the work done by the conservative forces is minus the change in potential energy. Okay, so that's for the 2 substitutions. So I'm just going to simplify this equation a little bit to say kinetic energy final minus kinetic energy initial. I just multiply the negative sign into the bracket, then I get minus P final, negative times negative, plus P initial, plus the conservative force. And if I change this equation around a little bit, I get that my conservative force is going to be equal to my final energy minus my initial energy, plus the final potential energy minus initial potential energy. And you should know by now, final minus initial is always equal to change in. So kinetic energy final minus kinetic energy initial will give me the change in kinetic energy. And kinetic potential energy minus potential energy initial will give me the change in potential energy. And from there I can actually see that my change in kinetic energy plus my change in potential energy is going to give me the amount of work done by non-conservative forces. So here I have a very handy tool to calculate work done by non-conservative forces. So at this stage, what do we have? We set the work done by the conservative forces. We have a way of dealing with that. We know that is minus the change in potential energy of the system. And now we also have a way to calculate the work done by non-conservative forces. So let's quickly look at an example where this is being applied. A man pushes a crate with a mass of 5 kg up an incline from a height of 2 meters above the ground from rest to 5 meters above the ground, where the crate has a speed of 1.5 meters per second. The work done by the friction force on the crate is negative 30 joules. Calculate the magnitude of work done by the man on the crate. I just redrew my whole situation on this page because so that I have a bit more space for my calculation. So what do we have? This man is pushing the crate. I've included the forces that's acting on this system. We know the normal force, the friction force, the force that the man is applying, as well as the gravitational force. His initial velocity is 0. His final velocity is 1.5 meters per second. And the amount of work done by the friction force they gave us is minus 30 joules. Okay, so if I look at the work done by the non-conservative forces, I know that's equal to the change in the kinetic energy plus the change in the potential energy. So what are my non-conservative forces acting on this block? It's my applied force, which I now just call, I called it FT, so that's why I call it WT over here. That T was supposed to be an A, in Afrikaans is toegepas, in English it's applied. Sorry for that little slip up. But anyway, the work done by the applied force, which is this one, they were there, plus the work done by the frictional force, those two are my two non-conservative forces acting on this system, is going to be equal to the change in kinetic energy plus the change in potential energy. So if I fill in all those values, I don't know what the work done by the applied force is. I know the work done by the frictional force. They gave me that as minus 30, so I can plug that in. I know my final velocity there is 1.5, so I put that into this half mv squared. It's a half times 5 times 1.5 squared, minus, luckily my initial velocity is 0, so that term is going to become 0. I pushed this crate from a distance of 2 meters above the ground to a distance of 5 meters above the ground. So my final kinetic energy is going to be the mass times the gravitational acceleration times the height, which is 5 in this case. In this case, the mass and the height is the same number, minus the mass again, which is the 5 kilograms, times the gravitational acceleration times 2, which is the height. And if I calculate all of that, I get my work done by my applied force is equal to 182.63 joules. Okay, here is an example you can try on your own. The diagram below, not drawn to scale, shows a vehicle with a mass of 1,500 kilograms that moves from rest at point A at the bottom of a rough slope. Point B is at the top of the slope, 200 meters vertically above the horizontal. The total work done by force F that moves the vehicle in 90 seconds from point A to point B is 4.8 times 10 to the power of 6 joule. The speed of the vehicle when it reaches point B is 25 meters per second. Use the energy principles to calculate the work done by the friction force on this vehicle. Why don't you try this problem? I think you'll probably have to watch this video 2 to 3 times because the whole idea of conservative and non-conservative forces are quite abstract, and we have derived a lot of theory from that. So be patient with yourself and spend the time to understand this. Good luck.